Greetings, I am the dark, shadowy figure that will be teaching you math today. Bwahahahaha. Well, that's much better. So, this is your first video. So, you should be watching me from home, I hope. And again, I'm going to go through our textbook, the interactive learning, about our first module, so 1.1. So I'm just going to make my head a little bit smaller. And our first module is about domain, range, and end behavior. So this is something that we're going to keep coming back to over and over again as we start to learn different functions and how they behave. We're going to want to know their domain, range, and end behavior of a function. So let's get started. Every one of our modules, they start off with a spark your learning. Some of them are kind of interesting. Some of them are really not. So, we'll see. Usually I talk about them. I don't always go over them in depth because I think there are times can be spent doing some other things. So, but this is a very interesting situation here, and it's something that you will see in science at least a whole lot, specifically physics. So we've got Pat and Sam are conducting an experiment involving a vertical spring on a weight attached to its end. They can only record data for a certain amount of time. And so you can see the little picture right there. This is a spring. It's technically a spring scale, but it's a spring. And then when you pull that spring down and you let go, it kind of oscillates back and forth. And so when it oscillates back and forth, that's when we get this type of approach. But apparently they can only record data from 0 to, I guess that's 13, 8, 9, no, I guess that's like 14 or 15 or something like that. And so, there's always this, what is a mathematical question that you can ask about the situation? What information would you need to know to answer your question? So a mathematical question, you could ask about what function this would be representing, how long until it stops moving, what is the maximum, minimum, and or or time length that this could be going. And most of those have to do with domain and range. So let's jump right into it and see how it goes. So here we are. Each lesson is divided up into tasks. And so you'll hear me refer to these things called task 1, task 2, things like that. There's typically about 4 or 5 tasks per lesson. So to get us started, we're talking about domain, range, and end behavior. So I mentioned earlier that you're going to see these words, domain, range, and end behavior, over and over and over again as we go through Algebra 2, as we be introduced to or reintroduced to different types of functions. It will always be important. It's like, oh, here's a new function. What is its domain? What is its range? And what is its end behavior? So it's kind of important to start by talking about these words and what they mean and what we're asking for it. But before we get there, whatever, we need to talk about intervals on a number line. So an interval, here's our vocabulary, an interval is an unbroken portion of the number line. So here's this long, lengthy, wonderful explanation that you can totally read, that I'm sure that everyone's going to read on your own time. But here is basically what we're talking about when we're talking about intervals. So remember, hopefully this is kind of review a little bit, but an interval is any section of the number line. So it can be, you can have 3 different types of intervals. So you can have a specific section like this. You can have a section that goes off into the negative side of infinity, I guess that way. You can have a section that goes off to the positive side of infinity. So these are 3 different types of intervals that we could be talking about. And notice that there are these like open circles, open circle, closed circle. And again, I'm hoping that this is a review. I'm hoping that you've seen this before, but hopefully you know that pictorially speaking, when you have a closed circle, this is the interval from A to B and it includes B. And the open circle, it is the interval from A to B, does not include A. So again, I'm hoping that this is kind of a review at this point, but open circle does not include A or whatever number this is at. Closed circle does include B or whatever number this is at. Okay? Okay, so let's look at how to write these intervals. So if we are going to write this interval, like I want to tell my audience or whatever that I'm talking about the interval from A to B does not include A but does include B, there's obviously going to be a more precise mathematical way of writing that. By the way, types of interval, finite, that's what we were talking about earlier. It's just one specific section. Infinite, infinitely negative, infinitely positive, things like that. But anyway, there's 3 different ways of writing each one of these intervals. So there's inequality notation, set notation, and interval notation. So we'll go through all 3 of these for all 3 of these situations. But here's some examples of what they're going to look like. So here we've got our interval. So if we were going to write that in inequality notation, that's this first one right here. So you always go either left from right or lowest to largest, I guess, or most negative to most positive, whatever. So you're going to start with your A. So you're going to have your A is less than X. X is typically our variable. Hopefully you remember that from Algebra 1. Oh, I can't write today. That's okay. Notice how I said A is less than X. So if we look at this less than there's no line underneath it. That tells us that it does not include A. So that open circle means that it does not include A. So we've got X is somewhere in here, and we know that X is greater than A, or A is less than X. So then to cap it up on this side, we would say X is less than or equal to B. So because this is a solid dot here, that's where we have the less than or equal to. So when it's a solid dot, it's less than, greater than, or equal to. When it is an open dot, it is just the less than or greater than symbol. So again, you go from left to right. So something like this would not be appropriate or would not be right. So we're going to put a big X through that. And I don't even know how you would do this, but something like, or no, go back. So something like this, that just kind of doesn't make sense because at that point you're talking about 2 different intervals. So anyway, also not right. Again, so inequality notation, A is less than X, which is less than or equal to B. So the second way of writing it, and this is the more formal way of writing it, it's called set notation. So we're not going to get into a lot of proofs in this class, but if and when you do get into proofs, you'll be using set notation a little bit more. So it's good to get used to it now. So again, for this top interval, for set notation, we use our curly brackets to indicate that this is a set notation, or this is a set. That's what the curly brackets mean. And so you're going to write it, and it's going to read as x such that a is less than x, which is less than or equal to b, close bracket. So again, it should look a little bit familiar with the inequality notation, but it's just a little bit more precise because it uses the curly brackets, which indicates you are dealing with a set of numbers, and that set of numbers is inside of this interval on the number line. So that is set notation. Again, we won't be using set notation that much in this class, but for this lesson, you need to know how to do it. Ha ha. So then there's the third way, and this is the way that I prefer, that I will do mostly, and you should be most comfortable with. It can also get a little confusing after a while too, and that is called interval notation. So I use it in this class the most because when you get into your next classes, or if you go away to college, this interval notation is going to become almost like a second language. And so when I was in calculus, actually, I struggled with, I just didn't recognize these things as intervals. And so it wasn't that I didn't understand the content, it was just I wasn't used to this language that my teacher was doing, and all of a sudden we were in the middle of a chapter and I was like, I don't know what you're saying. Anyway, so set notation, we're going to come back over here. So set notation is kind of an abbreviated way of describing an interval. I'm sorry, not set. An interval notation is an abbreviated way of precisely describing this interval right here. And so there's a couple of different ways that we use it. So we have a regular parenthesis, and that stands for, we'll put our A here, and that means that our interval goes from A to B, but it does not include A because we are using a regular parenthesis. But it does include B, so we're going to use square brackets. So the square bracket indicates that it does include this value. The curled ones, or the regular parentheses, indicates that it does not include this value. So this is something that you will see over and over again. So what gets confusing is when, let's pretend that this is an open circle as opposed to a closed circle. So then what would that look like? Hopefully you're thinking to yourself that would look something like this. This also looks like an ordered pair, you know, like your x and your y. But it's not, it's an interval. So be careful when you're looking at these things, and don't get so focused on, I see that it has to be a set notation, or I see that it has to be XY coordinate. No, like, be aware of your surroundings, young Padawan. Like, for real, like, just read the question and figure out what it's telling you. Is it talking about an interval, or is it talking about an XY coordinate? So, just a little word of advice. So that's the three different types of ways of writing an interval. So of course you can use all three of those ways to describe these other infinite intervals. So for like this one, you know, okay, so we've got our A. So if we're going to do inequality notation, so all of our x values is where the blue arrow is. They are all going to be less than A. So that's just going to look like x less than A, right? And we'll go ahead and do this bottom one too. We'll do that one in blue or green. We'll do green. So this bottom one here in green, all of our x values are greater than A. But can they be equal to A? Yes, they can. So what symbol would we use? It'd be x is greater than or equal to A. So again, hopefully you have seen these things before, but this is just how you would write it in inequality notation. So if we're going to be formal about it and write it in set notation, so again, it's going to look very similar to our inequality notation, except we're going to be all formal about it. We're dealing in a set, and we have x such that, that's that straight line, that means such that, x is, which one, is less than A, close bracket. So again, inside of the brackets is our set, and our set is x such that x is less than A. So then in green, for our inequality, we'll do, again, our set notation. We've got x such that x is greater than or equal to A, close bracket, which I totally missed, close bracket. So that's our formal set notation. So then if we wanted to write the same thing in our interval notation, which is what I think you should get used to, we would write, so this is A, but we go from left to right. So what does this arrow mean? What kind of number can we call that? Well, it's not really a number, it's technically a concept, but it is a negative infinity. So you will see infinity a lot this class, so get used to it. It's just a sideways 8. See if I can draw it a little bit better. There you go. So negative infinity to A. Now notice how we're using parentheses or not square brackets, because can you ever really include negative infinity? Not really. It's not really a number, it's a concept. So you will always have a regular parenthesis attached to an infinity. You will never, you will never see this. You will not ever, ever, ever see that. That is wrong. Because you can't include negative infinity. Because it's a concept, it's not a number. But anyway, that is what it looks like in set notation. So then in green, for our bottom one, so if we go from left to right, we've got our A, and then our A, our interval goes all the way up to positive infinity. So I can put a parenthesis right there because it's infinity. What are we going to put with the A? Hopefully you were thinking to yourself, a square bracket. That's all it is. So again, this chart is probably a really good thing for you guys to look at. I'm not going to say you need to memorize it per se, but you will use it enough to where it's going to be committed to memory. So just get used to it. So let's see what we can do with our answers here. Match each verbal description with intervals described in the table. All real numbers greater than or equal to A. So that one would be connected down to here. Greater than or equal to, square brackets. All real numbers less than A. All real numbers greater than A and less than or equal to B. And look, we even have a check. Yay! We got it right. An interval is modeled by the graph. Select the set notation and interval notation that describes the interval represented. So x such that x is greater than -1. So that one. And then -1 to positive infinity. By the way, I think this program, like this website that we're on, sometimes when you enter your answers, they might want a positive infinity. In real life, nobody writes it that way. You just put infinity, And if there's no negative sign in front of it, then it's insinuated that it is a positive infinity. But just know that you might need that plus sign there. Suppose a graph is changed so that x equals -1. The open circle becomes a solid circle. What do the set and interval notations change for the new interval? The set notation changes to x. Nope, that's not right. The set notation changes to x such that x is greater than or equal to -1. And the interval changes to that. We'll go with that one. Yay, good thinking. Think about how you can describe the set of all real numbers not shown in the graph in part B, and what its graph would look like. So think about how you can describe the set of all real numbers not shown in the graph in part B. Part B, graph, so the exact opposite of this. So it would include -1 and go to -infinity. So -1 to infinity, or -infinity to -1. It would include -1, and it's -infinity. We'll go with that one. Yay! All right, domain, range, and end behavior. Let's talk about what that means. So hopefully you've seen these words before, but maybe you might not remember them. I don't know. But as a reminder, recall that the domain of the function f of x is the set of all x values for which the function is defined unless additional restrictions are added. So the domain of the function is all the set of x values. So domain x values, domain x values, domain x values. If you haven't figured it out, I'm trying to give you a hint. The range is going to be the exact opposite, right? The range is a set of all values of f(x) that are outputted for the input domain values, otherwise known as the y values. So on a graph, the x values are your domain. All of the potential y values that you have are going to be your range. So domain, all of the x values that could possibly be entered into the function and you will get a real answer for. And the range is all of the potential answers that you could maybe get from the inputs. And then end behavior, I don't know if you guys went over that in Algebra 1 or not, but end behavior is exactly what it sounds like. It is, what does the end of that function do? Does it go up for infinity? Does it go down for infinity forever? Does it go straight in a straight line? You know, what does it do? Typically, we use words with like increasing, decreasing, stuff like that. So the end behavior of a function describes what happens to the values of f of x as x values increase without bound, or as they decrease without bound. So we have to be mathematically accurate here. So in this situation, we've got a straight line. We could say that the end behavior, let's see here, is that what we're talking about? So if you imagine the end behavior as you continue to go to the left here, you're just going to keep decreasing. It's a straight line, right? So you're still going to keep going down. So the way you would say that, as you would say, as x approaches infinity, f of x decreases without bound. As the value of x decreases without bound, the value of f of x decreases without bound. What you would actually write is something like this. As x approaches negative infinity, f of x approaches negative infinity. Okay? So this is more so what you would need to know how to write, per se. But what this means is as x approaches negative infinity, as x goes that way, because your values of x goes that way, f of x, or y, approaches negative infinity. So it keeps just going down. Without bound. So the other direction, As x approaches positive infinity, f of x approaches positive infinity. So again, it just increases. Too easy, right? Again, someday when you're doing homework like on the textbook here, you're getting something wrong like this, make sure you add like a positive infinity to whatever. So domain, range, and end behavior is pretty easy on a line. So let's try it on an actual, or I guess a non-line. So the graph of a quadratic function, so that's like x squared plus blah, 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 type of a function, is shown. So there's our function. So we're just going to go through domain, range, and end behavior, right? So our domain, what values of x could we possibly plug into an x squared function? So again, this is like x squared plus something x plus something else. And I'm sure I could figure it out if I wanted to, but I don't care that much. So what values of x could we plug into this function? The answer to that is we could plug anything we wanted into that. So I always like to try three things. 0, make something really, really negative, and then really, really positive. Really big positive number, really big negative number, and 0. So if we throw 0 in there, we're going to get C. If we throw negative 1 billion in there, we're going to get a number. I don't know what that number would be, but it would be a number, so that's fine. If we plugged in positive 1,100 trillion, you would still get a number, yes? So how can you verbally describe the domain of f of x? All real numbers. So that is all the values of x that we could plug into that function. So here's where it gets less easy. How can you verbally describe the range? So remember, the range is all of the values that we could potentially get on the other end of the function. So sometimes I like to think of these functions as computer programs. You have an input, that's your domain. You have an output, that's your range. So you can dump anything into this function. So then what is it going to come out? So the output, based on this graph, is any number 2 or above. So you're never, no matter what you dump into this function, you're never going to get 0. Never going to. It's impossible, according to this graph. So then when we look at our range, it would be all real numbers greater than or equal to 2. So then suppose, and this is end behavior right here. Suppose you could trace the curve of f of x left to right from its low points. Suppose you could trace the curve of f of x left to right from its low point. Think about how this would change if you could trace the curve of f of x right to left from its low point. What is the end behavior of f of x? I don't know, that's a really weird way of writing that, but whatever. As x approaches negative infinity, f of x approaches negative? No. So I'm going to eliminate this one too, because our f of x, they both go positive, right? So as x approaches negative infinity, f of x approaches positive infinity. Oh, that one's gone too. So hopefully this last one is right, or else we're in trouble. As x approaches negative infinity, f of x approaches positive infinity. As x approaches positive infinity, f of x approaches positive infinity. Here are my little scribbles. Yay. So the graph of an exponential function, g of x, is shown. Exponential function. That would be like a number raised to the power of x, or something like that. So how do the domain and range of g of x compare with the domain and range of f of x? Select all that apply. So let's look at the domain and range here real quick. So up here, we'll do it in blue. Our domain equals all real numbers. That is a cute little symbol for all real numbers. And our range is f of x greater than or equal to 2. Okay, so now we'll switch to red. So here, our domain, again, our function looks something like a number. Oh, I won't use 2. That might not be right. A number raised to the power of x. So what is our domain? What numbers can we shove into x? And the answer, you can either look at it analytically or you can look at it graphically. You can shove any number you want in there. There is no limitations to the x's that you can throw into this function. So our domain is, again, going to be all real numbers. That symbol looks better than my last one. So our range, however, is going to be slightly different. So this one right here, this is where you just kind of have to get used to it a little bit. This probably asymptotes at y equals 0. So it probably never hits 0. And I know that because I know how these functions work. And if you think about it, I mean, you can even throw this in your calculator. If you go really, 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 really negative, you're still not going to hit 0. There's no way that you can make this function hit 0. So our range, and I'm going to put this one in interval notation because interval notation is cool, is 0, does not include 0, and then it goes up to infinity. So if I put them all in interval notation, just because it's good practice. So this one down here, the range, we said f of x is greater than 2, so whatever this top one is, so let's see here. Okay, so there's all of our interval notation, our domain range and interval notation. Okay, so now we've got that, we can kind of compare them a little bit. The domain of g of x is the same as the domain of f of x. I'll agree to that. The domain of g of x is all real numbers, greater than 0. That's not right. The domain of g of x is all real numbers greater than 0. That's not right. The range of g of x is the same as the range of f of x. That's not right. I don't agree with that. The range of g of x is all real numbers greater than 0. Okay, I'll agree to that. While the range of f of x is all real numbers greater than or equal to 2. I'll agree to that one too. Yay! So then what is the end behavior of g of x? So again, if we look at g of x, so this approaches 0 as it goes negative, and then it approaches positive infinity as it goes positive. So as x approaches negative infinity, g of x does not approach negative infinity, so we don't have to worry about that. As x approaches negative infinity, g of x approaches 0. And as x approaches positive infinity, g of x approaches positive infinity. Woo! So again, domain is your x values, range is your y values, and end behavior is what does the graph do that way. So graph a function whose domain is restricted. So believe it or not, this is probably a little bit more realistic. Like you would come across something like this in real life because you're never going to have like these great, beautiful, easy to do functions you're only just going to have like a chunk of the function that matters to you. So like in physics, if you're measuring something with time, you can't have a negative time. That doesn't make sense. Like, what was the position at -3? Like, no, that's not a thing. You can't have a negative distance. So if you're measuring distances or something like that, you can have a negative number. So that's what they mean by whose domain is restricted. So we've got the graph of the function f of x equals 1/2 x minus 2 is shown for x is greater than or equal to 4. So here's our function. So when x equals 4, f of x equals 0, and then our end behavior. So it doesn't necessarily make sense for us to talk about what does f of x do whenever x approaches negative infinity, because it's not there. The domain is restricted. So the domain is just greater than 4, greater than or equal to 4. And so we can talk about the end behavior as x approaches positive infinity. F of x is going to continue to increase that way. Yeah, totally. I don't know. So yeah, totally makes sense. So use the graph of a function with the given domain restrictions to find the corresponding range. So here we have x squared minus 2x plus 2. So this is the actual function there. But the domain is restricted, set notation here, for x such that x is greater than or equal to 0. So how does the graph relate to the range? So again, you can still look at the graph. They're not asked about domain because their domain is this part right here. So our range is still, what is that, from 1 up to infinity. So our range is f of x such that f of x is greater than or equal to 1. And there was much rejoicing. However, for this one, the domain is cut short. You don't have that that vertex down here. So like the range for this function would have been the exact same whether you cut the domain or not. This one, they cut the domain x such that x is greater than 1. So this is all that you have. So our range now is f of x 2 and greater, not including 2, because that's an open circle. So range f of x such that f of x is greater than 2. Yay. Model a real-world situation with a function. So again, as I mentioned, when you get into the real world, it's very common to limit your domain for such things. So, for example, they said, blah, 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 blah. For example, the distance that a jogger travels at a constant speed of 6.5 miles per hour can be modeled by a linear function. Sometimes I wish I could run that fast. Anyway, so here's our linear function. When x is the time in hours jogged, the domain in this context is x such that x is greater than or equal to 0. So like, since x is a time, you can't run a negative amount of times. Like how do you do that? Like, oh, I'm going to go run -1 hours. No, that's not how that works. So again, just remember your context, especially in these word equations. A lot of times we just write down these numbers, and then we have all the stuff, and it's like, just read the actual problem and think about what they're asking about. So their example is they've got a home remodeling company is creating a kitchen island with a workspace countertop. The length of the countertop, so there's my little sketch. The length of the countertop is 3 feet greater than the width. So we've got our width plus 3. The width must be at least 20 inches. So the width must be greater than or equal to 20 inches to allow for sufficient workspace. So, if this rectangle right here were like super, super thin, you're not going to be able to do anything on it. So create and graph a model of the area function given these restrictions. Is it possible with the countertop to have an area of 7 square feet? Explain why or why not. Really? 7 square feet? It changed units on us. Jerks. Anyway, so the area, so if we were to model a function for the area of this rectangle, rectangles are length times width. So we would just do W times W plus 3 equals our area. If we wanted to simplify that, as all good mathematicians would do, so we've got something that looks like that. Then we could solve for an area of 7 square feet. So we've got W squared plus 3W equals 7. So then we would move that 7 over. W squared plus 3W minus 7 equals 0. Let's see here, is that going to be factorable? No. Not easily, at least. But it's graphable, right? So we can just shove it into our graphing calculator and see what we get. So this is a great opportunity to learn about our graphing calculator, right? So we want to graph this. So here I am in my graphing calculator. When you first turn it on, you probably have a screen like this. If you just go up here to your Y equals button, you're going to get a screen like this. Now, this on ours, it uses W's. You're going to have to use X's. So this is our variable button right here. So you're going to push X, and it's squared, plus 3x minus 7. And so I can get rid of my chicken scratch since I have it. So then you're going to push your graph button, and it will show your graph. So then from there, we can look at things like domain, range, and all that good stuff. But remember, we have a limited range or a limited domain, and so we would have to figure that out based on our graph. So let's see what questions they're going to ask. Oh, I guess we could answer this one at 7 square feet. So if I'm looking at my graph, I would find where x equals 7. 1, 2, 3, 4, 5, 6, 7. Oh no, it's off screen. So what we're going to do, we can just, some people like the zoom, some people don't. So I'm just going to zoom out real quick. Zoom out. Okay, so there it is. And then there's this trace function. So I push the trace. And so now that means that as I push left or right, it's going to stay on the function and it's just going to trace. So I'm going to go to what? Actually, I need to figure out where it crosses 0, right? So actually, I didn't really need to zoom out. Did I zoom in? I didn't zoom in. Zoom in. Okay, so we can trace some more, and we can get a little bit closer. So x is about 1.5. We'll call it 1.5. Bring all my chicken scratch back. So this W is approximately equal to 1.5 feet. So if we were to change that to inches, we're going to go back to, so I just push second quit to get back to my little normal screen. 1.5. There are 12 inches per foot. What number do we get? 18. So W is approximately equal to 18 inches. Notice that is not within our domain. So no, it is not possible based on these constraints. So we basically just did everything. Now they're going to walk us through it all as well. The area of the rectangle is given by length times width. So we had that one. Oops. Yay, great effort. The domain was given to us, W such that W is greater than or equal to 20. What? The width must be at least 20 inches to allow. Oh, but they're in feet. Always check your units. Yeah. NASA ran a probe into the moon once because they didn't check their units. What is the range of the function? Oh, that's a great question. So if W is 1.75 or 1 2/3, the range is going to be so what I would do is I would plug it into this equation. So let's do that real quick. So we're going to plug in, we're going to use this one. So 1 2/3 squared. I'm just plugging this in. 1 2/3 squared plus 3 times. Oh, I'm just going to turn this into a single fraction. So 5/3, and that's it. So that's going to be 5. So that's going to be 25 over 3. Over 3, there we go. And then whatever that equals. So we're gonna try that one, see if it works. Yay, look at that. How did you determine the descriptions for the domain and range? So we were given the domain and then we solved for the range. Sometimes you have to do that. So there's the graph of the function. So it looks similar to the one that we had, except it's just this chunk right here. How do the domain and range affect the way that you graph the function? Obviously, you don't have to graph things that are not in the domain and range. This is a secret for everybody who actually watched the video. We need a code word. So our code word is, how are you doing today, Mr. Lin? So if you say that to me on Monday, when you come in, I'll give you extra credit. I'll give you the equivalent of a full homework assignment of extra credit. I'll see you on Monday. Watch your videos.